Good afternoon and welcome to the SRS Image Stack Acquisition Webinar, MBF Bioscience's latest installment of our live web-based educational demonstrations. My name is Jose Maldonado. I am a staff scientist and research liaison here at MBF Bioscience, and I will be leading this demonstration today. The goal of this webinar is to highlight the benefits, uses, and features of the SRS Image Stack acquisition workflow, as well as to demonstrate its application. Broadly speaking, we will be considering the following today. What are SRS Image Stack series? Why would I want to use them? How do I generate a series of SRS image stacks using SRS Image Stack series workflow? Over the next hour, I will also take you through a step-by-step live demonstration on the use of SRS Image Stack series acquire workflow, with question periods throughout and after the live demonstration. For any questions not answered or addressed during our live demonstration, please visit our forum at forums.mbfbioscience.com. Alternatively, feel free to email us at info.mbfbioscience.com. Our demonstration must begin with a bit of background. The first question to address towards this end is simply, what is an image stack? Image stacks are high-resolution Z-stack images. Thin depth of field makes these images suitable for stereological analyses. In order to have these images be suitable for stereological analysis means that we must acquire them with a high-power objective lens. Using an objective lens with a high numerical aperture means that very small increments can be used between each Z-stack image. I'll have more on the use of high-powered objective lenses later in our demonstration. SRS Image Stack series, then, are a group of image stacks acquired in a systematic and random fashion and are suitable for stereological analysis. Image stacks are taken only where stereological probes will be placed. Image stacks can be analyzed offline on any Stereo Investigator Workstation. Let me expand a little bit on the topic of systematic random sampling. Systematic random sampling involves having the user determine or define the distribution of stereological probes, or in this case image stacks, but not their location. This graphic shows the placement of acquisition sites, illustrated as small black line squares, and their systematic placement in reference to each other within the user-defined contour. SRS distribution of sampling locations will be varied from one acquisition run to another, as the software decides where to place these sites. Acquiring an SRS image stack means that image stacks will be acquired from random locations, but their position relative to each other will always be determined by the user. Acquiring an SRS image stack series requires specialized microscopy hardware. Very basic hardware requirements include a high-resolution digital camera, motorized stage capable of directing movements in X, Y, and Z axis, a computer running MBF software to drive all of the motorized components of your microscope, and critically, high numerical aperture objectives. Let me expand on the topic of aperture and objectives a bit more. In order to discriminate one or multiple objects in tissue, we must use objectives with the ability to focus with a very thin depth of field. To achieve this, we must use an objective lens with a high numerical aperture. Use of a 60x or 100x oil objective is critical to stereological analyses where the discrimination of two closely spaced objects is required. An objective lens with a numerical aperture of 1.0 or 1.4 will allow the user to make these types of discriminations. In summary, high resolution and a thin depth of field aid in the ability to discriminate between objects which may be practically on top of each other. So as a microscopist, why use SRS Image Stack series? Well, there are a number of reasons. Fluorescent markers may fade very quickly when observed at high magnification. Prolonged observation of thin depth of field focal planes is often required in stereological analyses. Many commonly used fluorophores may bleach quickly and before analytical decisions can be made regarding the identity of single or co-labeled cells. And non-trivially, stereological analysis may in fact be time-consuming, making it difficult for labs to share microscopy resources efficiently. Image stacks, on the other hand, can be analyzed at the user's leisure without fear of signal degradation. Performing your stereological analysis on image stacks offline frees valuable microscopy hardware for other users or other analyses. SRS image stacks provide a digital record of tissue regions being sampled for stereological analyses. Also, the semi-automated hardware helps reduce user error over long acquisitions by engaging and disengaging appropriate hardware at the appropriate time. There are several compelling reasons for using SRS image acquire stacks. So, what does the SRS Image Stack series acquire workflow do? Simply put, it makes acquiring SRS image stacks very easy. The SRS Image Stack series acquire workflow takes users through the process of acquiring image stack series from multi-channel or bright field stained tissue, which are suitable for offline stereological analysis. The workflow is formed as a step-by-step guide helping users to do things such as trace their region of interest, empirically define their tissue thickness, define acquisition parameters, define stereological parameters, as well as saving these parameters for future use on other subjects in either the same experimental or control group. Before beginning any stereological analysis or image stack acquisition, users should have the following secured. Critically, sample tissue. The sample tissue must be free of all damage, including tears or missing tissue, and must always include the entire region of interest. The tissue, post-processing, should be thicker than the probe height plus the guard zone heights. Of critical importance is having your tissue stained thoroughly throughout the entire z-axis. Stained tissue which has or lacks staining in the central portion of its z-axis is not suitable for stereological analyses or SRS image stack acquisitions. Before beginning the SRS image stack acquisition workflow, users should also have such stereological parameters as counting frame, distribution, and counting frame size. Of course, calibrated stage hardware and software is important. By this we mean that your hardware should be calibrated both parcentrically and parfocally, and device command sequences should be delineated beforehand. Device command sequences are a series of commands which our software sends to the microscope hardware to initiate the movement and engagement of specific hardware pieces at specific times. So for example, a device command sequence may open an excitation light shutter, engage a fluorescent cube, and set the camera to specific exposure settings. Of course, we recommend having the latest version of Stereo Investigator, which as of this transmission is version 9.12. At this time, this is the end of our discussion of background topics. Please post any related questions you may have now before we begin our live demonstration of the SRS Image Stack acquisition workflow. So now, let's begin our live demonstration on how to acquire SRS Image Stack series using the SRS Image Stack series acquire workflow. In order to open the SRS acquire workflow, we must first have a live view. To this end, I will engage the camera by pressing the live view button and also engage my DAPI fluorescent filter. Great. I will use my video histogram to set my black and white points to try to obtain as optimal an image as possible. It is of some importance to not bleach your tissue while performing these types or these series of steps. So to this end, I will close my excitation light shutter until I'm ready to use my live image once again. The SRS Image Stack workflow is found under the Acquisition menu and is found here, as you can see. As you can see, the workflow is broken up into 3 subtopics: areas to acquire, acquire configuration, and finally acquire. I will begin with areas to acquire. Under areas to acquire, users will be prompted to enter subject information, set microscope to tracing magnification, and finally trace your region of interest. Let's go ahead and start that now. So for the purposes of this demonstration, I will enter my name, and I will choose a subject. The notes field is a useful place to enter notes regarding the subject or any other aspect of this sampling which may be useful to you or other users later in the future. If this is not the first acquisition run that you are performing on a subject, then you may wish to load pre-existing saved sampling parameters. As this is our first demonstration, we will not use existing sampling parameters, but rather enter our own. The first step is to enter the number of sections which we wish to analyze. For this demonstration, we will be analyzing and we will be acquiring images from one tissue section. It is possible to acquire images or SRS image stacks from multiple contours so long as they are on the same slide. This tissue was cut at 40 microns. The section cut thickness indicates or asks and requires not the post-processing tissue thickness, which will be observed at a later step, but rather the cut thickness which your sectioning device was set to. As we have only one section, we will leave our section evaluation interval as 1. The use of multiple sections would require you to enter then your section evaluation interval, whether it be 1 or some greater value. The tracing magnification, or step 2, directs the user to set the microscope hardware to the low power objective that's going to be used for tracing. In this case, I will be using the 2.5 objective to trace a region of striatum. Okay, I've set my hardware to 2.5 objective lens and verified that I have the same lens file as selected here in the drop-down menu. The next step is to trace my region of interest. For this, my first step will be to get a live view of my image. I'm choosing to use my DAPI channel because DAPI stained cells are the most numerous in this tissue and will give me the best chance at being able to delineate anatomical regions of interest. I will use my blue arrows to move my stage to find an edge which may be useful for me to begin my tracing. This is a good place. The serial section list lets me decide or select which tissue section I am working on. If my slide contained more than one tissue section and I wished to draw contours around more than one tissue section, I could select which section here. Alternatively, I have the option to add a new section now or edit information about the current section. I will pick the appropriately named contour, and if I choose to, I can even change the color. I'll now begin my tracing. As you can see, clicking outside of the auto move box moves the stage and my contour drawings together in such a way that the relationship between the contour and the anatomy being delineated remains together. Right-clicking opens up a dialog box which allows you to select Close Contour, thereby closing the traced contour. I will now close my excitation light shutter to preserve my tissue. Now that we have gone through the first subtopic, please post your questions now on any topic related to entering name and subject information, adjusting microscope to tracing magnification, and creating a closed contour around your region of interest. Shane has a question about how she can use pre-existing configurations. Let me go back to the workflow and show you how that would be done. One of the benefits of using the SRS Image Stack acquisition workflow is the ability to go back and forth between steps. Let me go back to step 1. If I did have a set of parameters I wish to use, I could simply click yes and then navigate to wherever that file may be found. Here is a set of parameters that I've saved from an earlier run. We will select no and go back to step 3. Genevieve has a question, that is the tracing evaluation interval entered in microns? I believe, Genevieve, what you're asking is related to the serial sections and their distribution from one to another. This is not entered in microns. This is entered in numbers of tissue sections. So if you had a series of tissue and you wish to analyze every 6th tissue section, then your tissue interval would be entered as such and not in microns. It's actually a unitless value. Okay, Sebastian is asking about having multiple regions of interest in the same section. Well, Sebastian, the way that our software works is that we use specific contours for specific anatomical regions. To that end, if you wanted to, let's say, outline striatum, hippocampus, and cortex all in the same tissue section, and acquire SRS image stacks that are going to be unique to each of those anatomical regions, what you do is you simply pick a different contour from the drop-down menu. So let's say that I wanted to trace striatum and hippocampus. After finishing tracing striatum, I would simply select hippocampus, return to my live view, move over to hippocampus, and then trace there. Okay, thank you for those questions. Let's move on now. The second subtopic in our acquisition workflow is the acquire configuration. This will help users configure microscope and software for acquiring SRS image stacks. It will help to empirically determine tissue thickness, select which contours we wish to be imaged if we've delineated more than one contour per section, set probe dimensions, and specify SRS grid dimensions. Step 4, or set acquire magnification, directs the user to move to the objective lens which will be used for acquisition. As we have mentioned before, it is critical to use a high-powered objective with a high numerical aperture. For this demonstration, I will be acquiring with a 100x oil objective, which I'm going to move to now. Clicking anywhere in the macro view with the left button will move the stage to that location. This can be useful if tracing edges need to be aligned with anatomy. To shift the region of interest, right-click to end joystick mode, select the Align Tracing button, click anywhere in the contour, and then click the location on the tissue where that position of the contour should be. One of the benefits of having semi-automated hardware is that it is possible to have hardware prompts appear in the software. For example, here, the software prompts us to finish adding oil or the change immersion oil before continuing. I am now adding a bit of oil to my slide and returning the stage to its working position. I use my video histogram to get an appropriate pixel excitation and then find my tissue by focusing. The software has kept track of the fact that I added immersion oil for my 63x objective, and so when moving to my 100x objective, no longer prompts me to do so. Fantastic. You can see here that the software has detected that we are using the 100x objective lens and has selected the appropriate lens file from the software. If your particular hardware does not have this type of communication ability, it is important to always manually drop down and select the appropriate lens. I'm going to go ahead and close my excitation light shutter once again to preserve my tissue staining. After we have set our microscope for acquisition power, we can hit Next Step. This step, or region selection, allows the user to select multiple regions, if available, to scan and acquire image stacks from. As we have selected only one region of interest, it is selected here. You could tell that it's selected by the fact that it's bounded by this white box. If you had multiple regions, they would appear in this work area as well. It's possible to simply hit Select All Regions to have them all selected, or unselect all regions, conversely. Once you have selected the regions of interest that you are interested in acquiring from, you may hit Next Step. This step, Step 6, Counting Frame Settings, prompts the user to enter their predetermined counting frame size. For this demonstration, we shall use a dimension of 15 by 15 microns. The actual dimensions that you will be using for your analysis must be determined empirically, and there is no standard value that I could offer at this time. Hovering the mouse over the counting frame turns the cursor into a four-headed arrow. Clicking and dragging sets the position of the counting frame in the location where it will be found during analysis. It's also possible to use the mouse to move each side of the counting frame wall. But as I mentioned earlier, we're going to use a 15 by 15 micron box. Once the user has entered the counting frame dimensions in X and Y, we can hit Next Step. Step 7, or SRS Grid Layout Settings, directs the user to enter the predetermined systematic dimensions for SRS layout. We've predetermined that for this demonstration, a layout of 1100 by 1800 would be sufficient. Alternatively, a user can use the Approximate Site option to enter the approximate number of sites that they wish to have in this contour. So for example, if a user entered 6 and press Estimate Grid Size, then the software would calculate an approximate grid size for that particular number of approximate grid sites. We're going to stick with our predetermined values. Step 8, or Image Stack Settings, directs the user to enter values related to the probe and to tissue acquisition. The first box here, labeled Collect the Following Set of Images, allows the user to collect images for either the mounted thickness, the probe and guard zone, or the probe only. The default option is for the entire mounted thickness. Some users may find it useful to gather the entire thickness of the tissue, while others will only want the probe and guard zones only. It is possible to collect additional images above your tissue by entering the desired value there, as well as below. Now we're ready to enter our image stack height information. The first step here is to empirically determine mounted thickness. For this, I will need to have a live view. So I will once again use my device command sequences to get my excitation light shutter open and get my DAPI cube in place. Pressing the mounted thickness set button brings up an ancillary menu that we can use to empirically determine our tissue thickness. The way I want to do this is to focus at the top of my tissue. I will use my Z meter to make sure that I am moving appropriately. And my favorite technique is to focus above the tissue until everything is out of focus, and then slowly come down until only a few objects are in focus. In my estimation, this is that location. I will then press Set Top of Section. I'll now want to focus down past the bottom of my tissue and focus up slowly until only a few objects are in focus. In my estimation, this is that Z position. I will now press Set Bottom of Section. When I press Add Measurements to List, a tissue height is calculated. Having an average mounted thickness measurement that reflects the reality of your tissue is critical to your stereological analyses. We recommend measuring thickness at various locations. One easy way to do this is to click anywhere inside of your contour in the macro view. You could then go to a location distant from the one you just measured and repeat the operation. As you can see, the software begins to calculate the average mounted thickness and export that over to the mounted thickness in the Enter Image Stack Height information box. The number of locations that you choose to measure thickness will vary depending on the size and area of your contour. The larger your contour is, the more locations you are going to want. If you believe that you generated a measurement in error and are confident that it does not truly reflect the tissue thickness at that region, you can select it here and delete it. Then you can repeat the measurement or move on to another location to measure there. After I am done measuring at various locations, I will once again close my excitation filter and now enter my probe values. We have predetermined that for this demonstration, a top guard zone of 3 microns and a probe height of 11 microns is suitable. The final option in step 8 is to enter a value for the distance between images. Depending on your hardware, the minimum value that you will enter here will vary. We recommend looking at your hardware specifications as well as the memory capabilities of your computer before making the decision of a step size. Other important considerations are the sizes of the objects that you wish to observe and count stereologically. We will proceed with a measurement of 1 micron step size. The final step, or step 9, directs the user to choose a location for saving the data and image files. So we have already entered a path here for a folder on my desktop. The next option is to give each of the images in your series a base. This makes it easier to go through and find a specific image, even an image that is part of a Z-stack later on. The images generated by the SRS Image Stack Acquire workflow will be titled whatever you name here, for example, webinar, followed by a series of numbers. In this way, each of the images of your Z-stacks will have a unique name and will be able at making it easier to identify and find it at a later time. If a user wishes to engage camera binning, they may do so here. We are going to go ahead and take images with our camera's highest resolution. The user can also pick the format to save their files in, specifically their image files. The options here are JPEG 2000 files or TIFF files. We at MBF strongly recommend using JPEG 2000. Finally, I will enter a file name for my data. At this point, I'd now like you to post your questions regarding selecting the region to be imaged, entering counting frame and SRS grid dimensions, image stack settings, or image file types and output locations. Jeffrey asks, what is the exhaustive grid option in the layout step? Jeffrey, for some highly infrequent events, such as, for example, co-labeling of BRDU and, let's say, NUN. For these types of events, it may be impractical to do a systematic and random image stack acquisition within one contour. Now, even if you are using serial sections that don't come one after the other, let's say that you were using tissue where your serial sections were every 6th section, you may want to exhaustively sample all of the BRDU stained cells in each of your sections. This essentially means that you want to count all of the BRDU positive labeled cells in this one region of interest. To that end, the exhaustive grid option makes it such that the entire area of your entire contour region of interest is imaged. In the end, when you do your analyses, you will be counting all of the low frequency events in each of your sections. So whereas it sounds like you may not be doing actual data estimation because you're counting every object, it's important to remember that you're counting every object on only those tissue sections which you are sampling. Sinan has a question about hardware, specifically the type of hard drives that should be used. We recommend that for the acquisition process, you write directly to an internal hard drive. We've had some users write their data to either networked drives or external USB drives. What we've encountered is that there is a potential for data buffer interrupts, or there may be some problem in writing to an external hard drive. This may result in some technical problems. Our recommendation is to always acquire your tissue and write the files directly to a local internal hard drive. Great. Thank you all for your questions. Let's move on now to our final submenu, which is the Acquire submenu. In the Acquire submenu, users will be prompted to specify pre-focusing locations, pre-focus to the top of tissue sections, save imaging configurations for future use, and also optimize camera settings for multi-channel fluorescent acquisitions. I will now go on to the next step, or step 10. In order to obtain SRS image stacks of your tissue from the top to the bottom Z position, it is important to indicate to the software the location in space of the top of your tissue. We recommend measuring at every acquisition site. In this way, you will have the most information about tissue top locations and have a greater chance of scanning and acquiring Z-stack images from the entirety of the Z axis. Alternatively, interactive site selection is possible. In interactive site selection, the user selects locations upon which to go through and measure tissue tops. By hitting the top of section button, The software will then take me to these locations where I will focus at the top of the tissue. A third option is to simply set the current Z position as the top of the tissue section. Using this option means that regardless of the true top Z position of your tissue, SRS Image Stack acquisition will always begin at whatever the Z position is now. I'm going to select to identify the section top at every site. Once again, we're using the technique of focusing up above the tissue and then coming down to focus along the top. Once the top of the tissue has been identified at all the predetermined locations, the user may hit Next Step. At this time, you may wish to save the sampling configurations which you've just entered. Doing so expedites the process of SRS Image Stack acquisition in the future by simply loading the grid size, counting frame, and various other values for future use. I will demonstrate how to save this. There, we have successfully saved these settings. The next time that I need to acquire image stacks from another subject of this group, whether it be control or experimental, I can simply use these settings by loading them up as you saw in step 1. Step 12 is the final step and is also known as the image acquire step. The acquisition list selects all of the regions or contours which you have delineated that are going to have image stacks sampled from them. As we have only delineated one contour, only one contour is listed and selected. Multiple contours would be listed here. The acquisition box allows the user to insert a delay time before acquiring each image. While we will not use this today, some users may find it helpful to have a delay between each image. One potential reason for having such is that stage movements may not become dampened before the next image is acquired. This may lead to blurry or out of focus images. If users find that this is the case, adding a delay time in between the acquisition of each image may solve the problem. As we are performing a multi-channel acquisition, I will select the multi-channel acquire box. I will then select multi-channel setup and pick the channels that I want to acquire. In the acquire setup box, I can define whether I would like red, green, and blue channels acquired, or any combination thereof. This tissue has both GFP and DAPI staining, and thus we will pick those two. Now, we must optimize our camera settings for each channel. To do that, we will use the multi-channel control, the camera settings box, as well as the video histogram. Our goal will be to use the exposure to achieve as broad a histogram as possible. I'll begin with the DAPI channel. First, I select DAPI under multi-channel control. I'm going to use my macro view to move to a representative location of tissue. I will then focus down. You will notice that as I move the exposure settings, the shape of the histogram changes. Optimal images will be achieved when the histogram is at its broadest along the x-axis. It's possible for users to adjust the black and white points as well as the gamma shift for this acquisition. The default button will bring you to the default values, and Optimize directs the software to pick what it believes to be an optimal value for black, white, and gamma. Moving to GFP will cause the software to save these settings. I will now switch to optimizing the GFP channel in the multi-channel control box. I will pick a lower exposure time and try to get as best a histogram as possible. Once I am satisfied that I have the optimal exposure and histogram settings, I want to close my excitation shutter once again to avoid bleaching. I would like to demonstrate that if I move from one channel to another, that the settings that we had predetermined for both exposure and histogram remain saved. Great. We're now ready to begin our acquisition. At this point, it would be useful to make sure that you are in no position to shake or move the table or platform which supports your microscope. To begin the acquisition, simply press click to start acquiring. The software will now direct the motorized hardware to engage the appropriate filters, the appropriate camera settings, and acquire the images in Z at each of your locations. As you can see from the bottom of the screen here, we are going to be acquiring at 4 locations. At this point, I'd now like you to post your questions regarding save your imaging settings for future acquisitions, selecting image file types and file output locations, or questions related to setting up your camera optimization step. Please post them now. So a number of users are asking why we recommend JPEG 2000 versus TIFF. Our engineers have been working towards improving our ability to handle specific image data files. We found that using JPEG 2000 results in very high quality images that are an order of magnitude smaller in size than conventional JPEG images. Also, our software works with JPEG images in such a way such that you will always retain your original data. Making modifications to things like brightness, contrast, or saturation levels will not actually change or modify the original data. In this way, it is always possible to go back to your original data that you have captured and look at it once again fresh. There's a question regarding acquiring multiple channel images without a motorized filter on a microscope. For those users that don't have a fully motorized microscopy system, our software is designed to work with this situation. What we do is we set up a series of device command sequences which simply prompt the user to engage the correct filter. So whereas the system I'm using now simply drives the microscope to make the movements and filter changes, what you would experience is a message telling you, now please move to this filter, or now please move to this other filter. Essentially, it can still be done, except it's done in a much more manual fashion. Great, thank you for your questions. Well, as we can see here, our acquisition is now done. I want to go ahead and close my excitation shutter once again. And now I will look at the acquire results. The acquire results box indicates to me that the acquire process has been completed. It tells me that all of my runs were completed, none were canceled, and none failed. I now want to go ahead and press I'm done. The software asks you if you're sure if you'd wish to close the workflow, which you can do knowing that your images and data files have already been saved. What you have just observed is a step-by-step live demonstration of the use of SRS Image Stack series acquire workflow. We believe that SRS Image Stack series are a useful method for analyzing multi-channel stained tissue offline. This methodology has many benefits, including a more efficient use of microscopy hardware, avoiding bleaching effect while analyzing your tissue, acting as a digital archive of your analysis, as well as being very easy to use. I'd now like to open up the questions for any final questions. Any questions that we do not answer today or which you perhaps do not think of today can be forwarded to us by either emailing us at info@mbfbioscience.com or by visiting our forum at forums.mbfbioscience.com. Hi, Genevieve. You're asking if we can demonstrate how to open our image stacks or how you open these acquired image stacks. These image stacks are acquired as a series of JPEGs or TIFFs and a DAT file. The DAT file contains information regarding the contour that you've generated and the location of Z stacks in that contour. These series of image stacks that you've generated can be opened by either directly opening the DAT file, in which case Stereo Investigator will automatically load the Z stacks at their correct position relative to the contour, or you can open the data file using our Optical Fractionator workflow. This topic of how to work with these files in one of these other workflows is a webinar all in and of itself. Kate has a very good question. She asks, does the software acquire images using one filter then the other, or does it switch back and forth between filters in each section? Kate, the answer to that is that it can do both, and it's up to the user to decide which of those two options they would prefer. Dana asks, what is the best way to transfer acquired data to a different workstation? Well, Dana, as we've already mentioned, we don't recommend you saving the acquisition directly to an external or networked drive. But once these image files are saved onto your local hard drive, you simply move the data file, the DAT file, and all the image files together to your workstation computer. There, you will open your DAT file, and the software will either prompt you to point out the folder where the images are at, or it's possible that your software and your DAT file and your images are in the same folder, in which case the program will find them there. Carlos asks a good question. Does the DAT file contain enough information that you would not need to define a lens on an offline system? Actually, Carlos, the information regarding the lens is on a separate file. It's a lens file, and we would recommend using the same lens information on a different workstation. So you would have to use a workstation that has the same lens file. Thank you very much for all of your questions and for your patience and your attention. We'd like to thank you for joining us for our latest installment of our web-based live demonstrations. My name is Jose Maldonado, and it's been a pleasure to help you. Have a good afternoon.